There are some equations that the skilled practitioner of physics keeps on hand that are not fundamental equations per se, but equations that are used to serve a practical purpose. And the reason why they exist is because in order to solve a problem, very often there's a great many steps involved. I start at part A of solving the problem. There's a traditional way I go through it to get to the final result. Well, in some cases, it's possible for me to realize that if I do some of those steps in advance, I can devise a formula that applies only in special cases, but is nonetheless useful for solving problems that occur quite commonly. So what I'm going to do now is I'm going to derive just such an equation. It's an equation that's used to find the range that a projectile travels when it is launched from an initial height of 0, which is not surprising because I can choose my coordinates such that I set the initial height equal to 0. But then it finishes at the same height, again, set equal to 0. So examples of this might be, for example, at a football game, a football is punted from the field level, it flies through the air in a parabolic trajectory, and lands again at the same height from which it was launched. So I'd like to know what is the range of that. That is, what is the distance that it travels horizontally. So what I'm going to do now is a derivation of that. Once I get done my derivation, I'll have an equation that is that answer and can be applied as long as I'm careful of the assumptions that I make along the way. In order for that to be useful to me, it's true, I'll have to memorize that result. So I'll have to have it in my head and ready to go at a moment's notice. We do physics for long enough, and some of these things sort of lodge their way into your mind. So if I'm going to find out how far a projectile goes horizontally, I'm going to start with a simple equation that's very familiar to anyone who's solved projectile motion. That is, the distance that a projectile travels horizontally, x, is the initial x position, which in principle I often choose when I'm solving a projectile motion problem to be equal to 0. Plus the x component of its velocity multiplied by time. There's a little understanding of projectile motion here in that what I realize is that the horizontal acceleration in projectile motion is equal to 0 in the case where I assume that there is no viscous drag acting, which would create a horizontal acceleration. But here in this example that I'm doing, there's no air resistance, and so there's no horizontal acceleration. And so the horizontal component of the projectile's motion is motion with constant velocity. As it happens, that constant velocity is the x component of the initial velocity, which I'll assert in just a second. But there are two things about this equation that I'd like to make note of. If I take the left-hand side of the equation and I subtract x naught, which appears on the right-hand side of the equation, what I get as a result is delta x, the horizontal displacement. And indeed, that's what I'm looking for in my equation. That's what I call capital R, the range of the projectile. But there's another assertion that I'd like to make, and it's one that I just said. In projectile motion, the x component of the velocity is constant for the entire motion. And so the x component of the velocity is the magnitude of the initial velocity multiplied by the cosine of the angle. That angle is measured to the horizontal. And so taking the initial velocity vector's magnitude and multiplying by the cosine of the angle gets me the x component of the velocity, which describes the x motion. So now I can take this equation right here and rewrite it as the range of the projectile by subtracting x naught over to the other side of the equation. The range of the projectile is equal to v0 cosine theta multiplied by t. I think I probably need some parentheses here. I don't want to make it seem like my t is inside of my cosine theta. What I wanted to do was to devise an equation for the range, and I'm well on my way, except I need to know the time of flight. I've already exhausted my description of the horizontal motion, because the horizontal motion of projectiles is quite simple. It's motion with constant velocity horizontally. So what I'll do is I'll investigate what I can find from the vertical motion of the projectile. That is a very familiar projectile motion equation. I've messed that up because I wrote y naught. That y is equal to y naught plus the initial y component of the velocity multiplied by time plus 1/2 of the y component of the acceleration multiplied by t squared. I hitched up a little bit there for myself because I didn't really want to write the y component of the acceleration, because I know that in projectile motion the y component of the acceleration is negative g, the acceleration due to gravity. So a couple of things that I'm going to do with this equation, all is not lost, I'll be okay. I'll just make some alterations. A couple of things that I realize about this is that I'm looking for the range of a projectile whose initial and final height are the same. That is, y and y naught are the same. Chances are I would choose them to be 0. But let's just write quite simply that no matter what, the final height and the initial height are equal to each other. So in this equation, they'll become 0. They'll go away. Also, I'll assert that the y component of the acceleration is equal to negative g. G is the symbol that stands in for 9.8 meters per second squared, the vertical acceleration produced by gravity. Another little thing that I can do to modify this equation in my favor is to realize that the initial y component of the velocity is equal to the initial velocity multiplied by the sine of the launch angle. Here I had, well, up above here, I had related it to the cosine of the launch angle. Here the vertical y component is the sine of the launch angle. So I'm going to make all those substitutions here in my main equation. That is, y is equal to y naught, I'll make both of those 0. V naught y, I'll make v naught sine theta. And 1/2 ay, that ay will be negative g t squared. So here come a lot of changes all at once. I'm going to write this as v naught times the sine of theta. That multiplied by t is equal to 1/2 g times t squared. Now, I took a lot of algebraic steps there all at once. Because there was a negative sign here, I simply shifted it over to the other side where there was a 0, and a lot happened in that one step. But nevertheless, I see what I have now is a relationship that involves t. Again, the reason why I'm doing this is because the unknown t appears there in my range equation. So I'm going for an expression for t. Notice that I have a t on this side of the equation, which will cancel one of the t's that appears on this side of the equation. So multiplying the 2 to the other side, I might write this as 2 times v naught sine theta is equal to g times t. So I have what I was looking for. I wanted an expression for t. It's not necessarily a pretty one, but t is equal to 2 v0 sine theta divided by g. Now I'm going to take this expression for t and bring it back to my range equation, which was my goal. Here I have the range is equal to v0 times the cosine of theta multiplied by t. Well, now, instead of just having t, I'm going to replace it with what I know t to be equal to, which is 2 v0 times the sine of theta divided by g. And as often is the case with this sort of derivation, I'm done now. I got the equation that I wanted. I'm not going to make any more substitutions. However, it's very common to write an equation like this one in a more compact form, because the more compact form is easier to memorize and has greater utility to use. So I'm going to realize what I have going on in the numerator. I have a v0 times a v0. That's going to give me a v0 squared. And I have a g in the denominator, so I'm going to get a g in the denominator there. Now what that leaves me with in the numerator is 2 times sine theta times the cosine of theta. Now there's a trigonometric identity that I spot here, and maybe you do as well if you've studied your trigonometry carefully enough. If you're trigonometry teacher was sadistic enough to make you memorize such things. But there is a trigonometric identity associated with 2 sine theta cosine theta, and that's actually equal to the sine, it's not the best job I've ever done there, of 2 theta. So the sine of 2 theta, you know what? I can't even stand it. So if you'll pardon me for just a moment, I'm going to go ahead and scrub that out and fix it. So I'll talk while I fix it. So I've written parentheses here around the 2 theta, and the reason for that is that I want to make sure that it is twice the angle that I'm referring to. Because, well, here's a quick result that I can get. I might wonder that if this is the equation for the range of a projectile, what angle should I launch a projectile at so that it's the maximum possible range? Well, that's going to happen when the sine function here has the maximum possible value. Well, the maximum value of the sine, of course, is 1. Sine functions vary between 1 and -1. So to get the maximum value out of the sine, I want the sine to have a value of 1. Well, that happens at 90 degrees. So twice the angle that appears in the argument, that would have to be equal to 90 degrees. So if twice 90 degrees is equal to the angle of interest, then the angle of interest is half of 90 degrees. That is 45 degrees. And I see in this expression a result that I might have actually guessed, that in order to get the maximum range from a projectile, I fire the projectile at 45 degrees. Any higher, and it lands shorter. Any lower, and again, it lands shorter. It might be of interest to you to plot some trajectories to see what they look like at different angles. You'll get a very good visual sense of how they distribute themselves. So this is my range equation, and if I can remember it, it saves me all of this algebra that I just did to derive it. And I can just sort of cut to the chase. Notice that it does not have the time in it. There's no time anywhere in the equation. So in a problem where I'm not given the time, there might be great utility in using this expression. Also, it relies only on knowing the magnitude of the initial velocity and not its components. I might find also in using this equation in practical purpose that that is of great utility as well.